I'm Danny Merino. I'm the R&D lead inside of Project InnerSpace, and I'm very pleased to welcome you to our demonstration of GeoMap Beta. Many of you probably know us already, know that our mission is to break the barriers that are in front of the growth of geothermal to terawatts of energy. And today we're going to be talking about GeoMap as a solution to the barrier of data availability. Because at the beginning of the project, it was clear that there was no global atlas available that could help stakeholders to understand the potential of geothermal worldwide, to understand what are the regions around the world that can have more penetration of geothermal, or where geothermal can have the most impact, particularly in those regions where we know that the demand will grow, the demand of clean energy will grow with time over the next decades. It was also clear that not many entities would have the incentive to dedicate funds to this endeavor, particularly considering that our ambition was to create something that would be open, access, free, accessible to every single stakeholder, you name it, between investors, researchers, policymakers, educators, entrepreneurs, industrial developers. We wanted to make this accessible to everyone. So as in Project InnerSpace, we created an alliance, a partnership with Google Earth Engine and with Google Cloud to develop GeoMap. And in the end, GeoMap comprises three things. One is the outcome of our portfolio of R&D projects covering worldwide subsurface data. It also includes surface data coming from Google. And in the end, we have created a techno-economic sensitivity tool to merge the information from the subsurface and surface so that people can understand how the coupling of the two can have an impact on geothermal economics. What we're demonstrating today is what we call beta for GeoMap, because GeoMap will have a development over the next months in phases, increasing the number of functionalities, increasing the complexity, but also increasing the data availability continent by continent over the next months. But this first version, our beta, is focused on Africa as a first case study of a region where we can use this tool to highlight the potential of geothermal in a region of the world that we know that is going to grow dramatically in terms of energy demand. So the screenplay for today will start with a demonstration of what we have right now in the tool in terms of subsurface capabilities. Helen Doran will lead that together with the subject matter experts that are responsible for the different layers inside of the map. We will move with Stephen Lee to talk about our surface model, and the mic will come back to me to talk about techno-economics. A little bit of housekeeping. After each one of the presentations, we will have the opportunity to have a Q&A, questions and answers. So every half an hour, there will be a break for questions and answers. What we invite you is to write your questions in the chat in a way that we can moderate and select maybe what has a greater impact for the conversation. So please keep your microphones off and we communicate through the chat. And without further ado, let me pass the mic to Helen to get started with the subsurface module.
Welcome, everyone. I'm Helen Doran. I'm the lead geologist at Project InnerSpace. And as the slide tells you, I am going to talk about the subsurface module, which is one of the three modules we'll talk about today. But before we get into the tool and the demo, I wanted to actually start with a little bit about the background research to the project that we're running at Project InnerSpace. And I'm really delighted today. We have representatives from our funded research program on the call, and they're here to answer your questions, and please put them in the chat, as Danny said. Very early on, when we were designing the research, we recognized that no one single institution could manage the scope of understanding the variations in surface heat flow across the Earth. So consequently, and very deliberately, our research program engaged multiple institutions, and we now have 85 scientists, global experts from over 10 different universities, companies, various consultancy groups working across the globe to help deliver our designed funded research program. And the research method that we designed means that we manage it, we engage these top-tier global experts, but more importantly, we designed it to recognize and build the foundation of the exploration triangle. And that's the diagram you see in front of you. And this triangle is the same as you get in oil and gas, the same as I see developed for CCUS, for hydrogen, and it's a way of building the foundations in each level to that we're not missing pieces, and we can get a clearer and clearer idea of where we focus on as we get closer and closer to that prospect level. So the GeoMap and the data layers that you see in GeoMap really address the first two layers. And there's a difference between those two layers. The first layer, the bottom layer, is all about understanding the different layers of the crust. These are the different layers of the earth, the crust, the mantle, and the sediments. These are things that we cannot see, that we often have to use inversion techniques or geophysical techniques to understand. And a lot of the projects that you hear about today address those layers. So how thick is the crust, the sediment pile, the depth of the mantle, what's the conductivity and the variations in those. And we couple that with the second layer, which is more observationally driven. So these are things like the advection, the things we see in the surface, volcanoes, geysers, igneous intrusions, moving and active faults. And between those two layers, we develop, or we start to think about where geothermal is favorable in the subsurface. And that's essentially where we get to with the GeoMap product. Moving up the triangle will be a focus in later years, or next year, essentially. But in order to know where to move up the triangle, you need to understand the base, because that helps you focus and helps you understand where you dedicate both resources and funding towards. And that's what we'll be looking to do as we roll and move forward in the future. So that's essentially what the map product is. We get halfway up the exploration triangle. It is designed to highlight areas of geothermal favorability that then we can do deeper dives and more work on top of. So we started this journey with Africa, the continent of Africa. And I often get asked, why did you start with Africa? Because in many respects, it's very difficult. A lot of data is behind paywall. It's not freely accessible. There isn't large amounts of collaboration to release large data sets across multiple countries. But in a way, Africa is pivotal. It is part of the energy transition. It's part of growing population centers. And if we can build data and understanding there, in theory, we can do it anywhere else. So that's why we started with Africa. It was difficult, and a lot of the work, you have to create data from scratch, and Paul will talk about that later on today, hopefully. But we will then roll out, where the team are currently actually working North America and South America, and then we'll move across to Southeast Asia, Europe, and finally Oceania. And where we work in the world is driven by population centers, by energy demand, and that's what's dictated the pattern of how we roll these continents out. Now, we will be rolling them with time. We will publish on our social media when we release them into the map. We often get asked when the data will be available to download. We appreciate that all the scientists that work with the data want to bring it into their own programs to utilize it in modeling, and that will be available in the future, but we have to respect the scientists that produce the data, and we must go through the right pathways to create proper citations, put this data into a robust review process, and publish the data before we can release it. So bear with us on the release of the data, and that will come. So the next step is to do a demo. So this can probably only go wrong, doing a live demo, but I'm going to give it a go. If I stop sharing this screen. Okay, so this is the online map-based product that you can all gain access to for free just by utilizing the Project InnerSpace website. On the left-hand panel is what we call the data library, and I'm moving my mouse and hopefully you can see it. We have two modules in there. One is a weighted overlay analysis, and then you'll see the subsurface and the surface modules. And of course, I'm talking about the subsurface module today. Each of those modules are further divided by geographies, and that's dictated by our rollout. As you can see, Africa under the subsurface is the most complete. If we expand on those, in the subsurface module, each of these are then further divided into 4 sublayers. And these layers are really highlighting 4 elements that we need to fully understand to determine geothermal favorability. So in each of these geographies, you'll have a tectonics, an advection layer, heat source, proximity, and a heat flow layer. As you can expand in these, you'll see in the tectonics, probably very intuitively, you have faults and a number of crustal facies. Every layer that's in here has an information tab associated with it. The idea is that this platform is both interactive but also educational. So why are these layers important for understanding geothermal? And there's a description of why. There is also a description of how the layer was built and importantly, a citation for each of the layers. The layers can be viewed in stacked multiple systems. You can toggle on and off. There's a number of functionalities in terms of how you want to navigate around the globe, spin it. There are different default settings. Some of the data is much better viewed in a lighter setting. Some is much more powerful to view it in a satellite. You can have a flat base map or a globe. We can also input any latitude, longitude that you would like to look at. So for example, if you're an industrial partner and you want to understand the geothermal favorability in, say, your plant, your distillery, your data center, you can put in the lat long and zoom right into that location. For many of the layers, for the geologists, there's actually a hill shade layer, which makes viewing several of the more detailed geological layers much more attractive. Like here we have the shear wave speed, shear wave velocity speed. There's also a tool to query the layers, so you can get a value for each of the layers. And you can also view multiple layers on top of each other. So here you may notice, the geophysicists amongst you may notice that there's a very strong positive correlation between the shear wave velocity and the occurrence of volcanoes, and that is true for anywhere globally. That's why understanding that is very important. Okay, I'm going to pass the first question over to Sven, who will introduce himself and address one of the questions we get asked a lot. Actually, is we have a large funded project with the International Heat Flow Commission, and we get asked a lot about what are the details behind the project and the project goals and the objectives. So Sven, over to you, and I'll let you address those, and I'll click the slide as you wish.
Yeah. Thanks, Helen. Hello to the audience. So my name is Sven Fuchs. I'm a scientist at the GFZ Potsdam in Germany, and I'm a member and the vice chair of the International Heat Flow Commission. So in this function, I'm also the custodian, and I'm responsible with my team for the global heat flow database itself. So thanks to Project InnerSpace, we are in a process that we accelerating the so-called global heat flow data assessment project. So that means we are collecting heat flow data for more than 60 years now. That's quite a long time. And we are in the process of transforming those data into a quality controlled, quality assessed database. And somehow transforming all these years of research into something useful also for geothermal exploration. What are we doing actually? So we are a global collaboration of scientists. It's not only one institute. We are dozens of scientists and supporters that are working mainly on new standards for heat flow. So in the past months and years, we defined new standards for heat flow data structure. So what is a good heat flow value is the question behind. We also defined new standards for the quality of heat flow, and those new standards means that we need to reassess and restructure all the available data. So we are doing this right now since early last year together with Project InnerSpace. And our goal is really that we create a data set that can be easily used with the goal of geothermal exploration, but also can be analyzed with sufficient metadata with the specific scientific questions of each of your geoscientists or biologists. So the overall project is organized by the IHFC, so the International Heat Flow Commission, as part of the IUGG. and also by the International Leadership Program in GT. Thanks.
Thanks, Sven. And we have a second query, actually, that comes in quite a bit in terms of the tectonic element layers. What data goes into those? So if Paul is on the call, can you address that one?
Hi, Helen. Thank you. So hi, everyone. My name's Paul Markwick, and with Douglas Payton and his teams up in Scotland and over in New Mexico and China, we've been building the structural and tectonic databases. And the inputs for these are varied. And as you can see from this figure, the primary data are data sets such as Landsat, radar data, which was captured by the shuttle missions, and then gravity and magnetic data. And those are data sets that are publicly available, and we analyze and interpret to build up the structural model and the crustal model and the igneous interpretations. That's supported by other data sets, such as seismicity and seismic data. But then it's also secondary information, or what we call secondary information, which is the published literature. And this is an incredible, powerful resource. And what we use this for is to add information about the age of features, their activity, and also with the igneous rocks, what their composition is. So it's building all of those different data sets, putting them together, and from those building this new data set.
Thank you, Paul. Thanks. And next is we'll hear from Megan, who is responsible for the sedimentary thickness layer. And again, Megan, just a little bit of detail of the methodology, the input data, and why is it different to what is already in the public domain would be great.
Great, thanks, Helen. Hi, everyone. My name's Megan Holtz, and as Helen mentioned, I'm looking at constraining sedimentary thickness. To explain the methodology in more detail, I chose the Karoo Basin, which is the southernmost basin onshore South Africa. And on the screen, you can see two grids. On the left-hand side, you can see the global sedimentary thickness grid from Lasker and Masters, and on the right-hand side, we have the grid and the constraints from our study. Essentially, we're taking a very data-driven approach. So we're using seismic and well data to constrain sedimentary thickness. And on the map on the right, the wells are the circles and the seismic are the lines. And you can see from this example, our data suggests that the basin reaches a maximum thickness of around 9 kilometers, which, if you compare to the map on the left, is a significant change from existing global sedimentary thickness grids. And I would say, compared to previous grids, we're able to more accurately constrain the depth to basement because we're taking this data-driven approach. And we also see more variability laterally, particularly in the smaller basins, because our grid resolution is 0.03 degrees, while existing grids typically have a resolution of around 1 degree. If we go to the next slide, the other advantage is that we're also providing metadata alongside the grid. So the first piece of information is we're providing the location of the data. So this means that the end user can see where we have constraints and where the grid is simply an interpolation between measurements. And this is really important because there'll be more uncertainty in the areas where it's an interpolation between measurements and less uncertainty where we have the data constraints. The other piece of information is the type of data. You can see on the right, on the map on the screen, the wells are in pink, the seismic reflection lines are in blue, and the seismic wide angle refraction lines are in red. So you'll have information on the type of data constraining the grid. And finally, we'll also provide information on the original source of the data. So in the case of the Karoo, there were about 6 different studies that I used to generate this grid, and this information or these studies will be available. So you can dive into these studies. You might like to learn information on the temperatures encountered by the wells, or more information on the structure of the basin from the seismic lines, and the metadata will guide the end user to more information. So really, the metadata will be incredibly useful for a variety of reasons, whether it's to understand more on the uncertainties of the grid or to use it as a launch pad to understand more about a particular basin.
Thank you, Megan. And I should add that currently in the GeoMap, the Megan's metadata layers in terms of the seismic and wells aren't added, but they will be added in the very near future, so people can interrogate those in addition to the beautiful grid that's been created. A very recent add to the GeoMap product, in fact, just hot off the press this week, was a series of fault, polygon, and stress data. And this was work done by RM Geology, one of our funded projects. So I would like to invite Mikael to address why is this important for geothermal? Why did we do this piece of research?
Hello. As Helen said, my name is Michal Demchuk, and I lead a group of structural geologists working here at RM Geology. What we've done, we took maps generated by groups which were introduced by Paul a little bit early on, which provided maps of crustal facies distribution and maps of structural architecture. And we basically put together two data sets. This one interpreted into fault polygons, and we combined it with data from world stress map. So once we created polygons, we could know what type of stress datum characterizing in situ stress is present there, whether it's earthquake focal mechanism based one, borehole breakout based one, drilling induced fractures based one, overcoring hydrofractures, or just geological indicators. When you look at the left-hand panel, it's green polygons showing upper crustal fault blocks, which indicate that there is a stress datum available in the database for that particular polygon. We've also color-coded earthquake-based stress data separately. It's not shown here, but it's a separate color, simply indicating that there is an active fault forming one of the boundaries of a respective polygon, or active fault inside of that upper crustal fault block. Regarding interpretation of polygons, we needed to make several assumptions. So we assumed granitic rheology for upper crust. For sediments, we assumed dolomitic rheology. It simply helped us to interpret fault polygons in same fashion, something really brittle. So if there are two interacting faults, linkage between would be the closest possible distance covered. With this fashion of interpretation, we started with the smallest blocks and advanced towards larger ones. And I think that's pretty much all I can tell you at the moment.
Thanks, Mikael. Before we move to Javier, who is our integrator in the project, there's a few questions, and I think I can address 5 of them with one answer, because it is the question we most frequently get asked: when can we download the data? And I mentioned it just before, but I'll reiterate. All the data will be open access, Creative Commons, no issue accessing it. It'll all be in the public domain. But in order to put it there, it has to be correctly reviewed, cited, and with a DOI. So bear with us just as our research teams get to that comfort level that we can put it out, but it will be put out into the public domain. So I think that's like 6 questions of the same. There's a few others that we can address. I think Javier will touch on one of them. So Javier, I'd like to welcome you in. So Javier is responsible for the inversion modeling, so he is the ultimate integrator in our product or in our project. A number of the layers that we create, whether it be sediment thickness, crustal facies, depth to basement, will be integrated into his model. So he will touch a little bit on his surface heat flow model, which will address one of the questions, and then I can deal with the rest. So Javier, can you introduce yourself and say a little bit about how you integrate the different pieces of work into your product?
Yes, hi Helen, thank you. So my name is Javier Fourier. I'm a geophysicist, and as Helen said, and my role here is to construct as good as possible a temperature model for the lithosphere, and in particular for the crust. The top few kilometers of the crust is what is most relevant for geothermal energy. But in order to get right this bit, we need to follow a bottom-to-top approach. We need to understand what's a lithospheric structure, the thermal thickness of the lithosphere, the outer rigid unit of the Earth acting in plate tectonics is very relevant. It controls the amount of heat that goes at the base of the crust. So in order to get an understanding of this, we need to use the best seismic tomography data that this, which for this matter is surface waves, in particular Rayleigh and Love waves propagating throughout the lithosphere. This we do in collaboration with a seismology group led by Sergei Lebedev in University of Cambridge. He's not here, but it's an essential part of the project. And what we don't want to obtain simply velocity models that then are turning to temperature. We directly want to invert the surface wave data into temperatures. And for that, we use what we call an integrated geophysical petrological approach, where some of the key properties in the mantle, for instance, seismic velocities or densities, are computed based on thermodynamics, temperature, pressure, and composition. This is one element. The other element is understanding what happens with the crust. And for that, we need to know how thick is the crust. Is there a sedimentary layer? How thick it is? What is the lithology? We need to understand, in order to constrain the geotherm, what is the thermal conductivity and what is the radiogenic heat production. So these are things that we have less control with the surface wave data that we are jointly inverting with other measurements. But we can use external independent information, like what Megan mentioned, for instance, independent information on sedimentary thickness that can be built into the model, also crustal thickness. This is important because in the models as we have them now, we just distinguish 3 layers within the crust with different thermal properties, but this is not enough. We know that this varies laterally with lithology, and this is what we are currently doing, incorporating lithological model in the crust that also tell us something about the heat production and thermal conductivity. Finally, we need to validate our results, and we do that with high quality surface heat flow and borehole temperature data. So it's essential to make it right. And this we have a students group in GFZ working on high quality filtering of the data, because of course we need to just constrain what is affected by the lithospheric structure, which is the map that is on there. It's basically a lithospheric prediction. It's not a real heat flow, it's a prediction from the lithospheric structure. On top of that, there will be other perturbations related to the surface, but this is okay. We want to have a prediction of the heat coming from the lithosphere. I think that's more or less my bit.
Yep, perfect. Thank you. Yes, thank you, Javier. And it touches a little bit on one of the questions that have been asked in the chat. So can you tell more about the geothermal gradient map and how is it going to evolve in future versions? And that's definitely something that will evolve in future versions. The current version is very simplistic. It's based on Lukazu's 2019 surface heat flow, plus variations in conductivity in different related to cratons versus sedimentary basins with and without salt. It's that simple. The entire idea of all of this research combined means that we should be able to put out a much, much more robust geothermal gradient map. And that's something that we'll be looking to do in the future. There's a comment here on the difference between conduction and adding in convection. That's, of course, more difficult. Most of the geothermal gradient maps, it's easier to deal with conduction, but we have some ideas of how to build in convection into that as well. So the plan, or when those will be delivered, probably at least another 6 months, unfortunately. Paul, finally, very briefly, in areas of no pre-existing data, how do you build the database? And I guess Africa is a perfect place to have case studies on this.
Yeah, Africa's, and it's a reason for starting in Africa, because the databases need to be consistent globally. And so you really want to test out in an area that you don't always have a lot of data. And that's actually why we had this example as well from Hogar, the mountains in North Africa, to just check that everything worked. And again, it's very much building up from those remote sensing data sets, building up the structural framework, adding in information about what the interpretation was based on. This is our audit information. And this is the big difference from a lot of other data sets, is you can always go back and check to see what this is based on. And then adding the crust composition and thickness and the igneous activity. But essentially it's going into these areas where we don't have data, because that's where we might find something. You know, it's where we don't have that information at the current time.
Exactly. It's going beyond the obvious and where we know. Exactly. Okay, I think that's a wrap for the subsurface module.
Thank you, Helen. So yeah, just to briefly touch on the partnership with Google. Sorry, Helen, I overrode your slides. I think I actually have that slide somewhere, but I'll come back to it. But to briefly add, we're working closely with Google Cloud and Google Earth Engine engineers to both host our app, but to help with our geospatial analyses, specifically with our weighted overlay analyses. And we have some additional plans coming down the pike for how to collaborate with them further. They really have, well, as we all may know, phenomenal compute resources and fantastic software engineering talent, both spanning machine learning and geospatial analysis. And Google Earth Engine has been really a crucial tool to help us with our raster processing. So we're excited to be working with them and to actually, at some point, potentially evaluate other sites for geothermal that pertain to Google demand for electricity and for energy, specifically with regards to, well, their data centers and things like that. They actually had an announcement recently about their first pilot with actually a startup. So this is an exciting collaboration for us, and I'll touch back on that in a little bit. I'm here today to talk about the surface module, which is one of the 3 parts of our presentations today. Thanks, Helen, for the introduction. The purpose of the surface module is to complement the subsurface module that Helen just introduced, and aggregate surface-relevant geospatial layers that may influence geothermal project planning downstream. And we have a number of different surface layers, both existing that are already in the tool, and planned that are going to be rolled out in phases in the upcoming months. And we'll talk through most of these one by one, especially the existing layers here. But at a high level, these layers are relevant to topography and resources, infrastructure, demand, weighted overlay analyses that kind of combine all of these different views, and additionally land use and policy, which are coming in short order. So I'm going to now switch and briefly do a tool demonstration, just showing some of the surface relevant layers. Helen already introduced a lot of the interface of the tool. Specifically, I wanted to start by looking at different borehole and seismic mapping layers that we've included. So our existing boreholes are shown as these black circles here. The 2D seismic surveys are these red lines, and 3D seismic surveys are these blue polygons that are showing on your screen. And essentially, what we're trying to do is provide a very high-level view, actually, to help users who may find a lot of subsurface information, especially what Helen has introduced in her team, if they found those layers to be useful and they actually want to do further analyses into seeing whether data is out there, they can kind of follow up and drill down into these different resources. So all of the boreholes, 2D and 3D seismic scans, came from a company called MapStand. In addition to, for the US, the borehole layer came from the US Geoscience Information Network. And again, they're really intended to give a starting point for knowing where it's relatively easy to pay to find more subsurface information. So for instance, if you wanted to plan a geothermal site, you can potentially de-risk that site by getting information from nearby existing surveys and boreholes without having to commission your own sensing or digging investigations. And we think it's a fairly comprehensive data set that we're showing. And I can click around a little bit, and you can see some information about sites of interest. So right around Nigeria, we're finding a couple of 2D and 3D seismic surveys. And for instance, someone can go and either Google and search for, or discuss with MapStand how to trace down some of these previous surveys, and they can get more information on that. The same goes for these boreholes. So a few other layers that we wanted to introduce with the surface module pertain to slope angle, and I'll start with just that. So the idea here is that, well, we have all of the Earth's surface, and we actually have topography information that comes from satellite data. And as a derivative product, here we have slope angle, which is calculated from that topography information. The legend is shown on the left-hand side over here, if you can see it. Blue would correspond to areas with lower slope, and redder areas would correspond to areas with higher slope. And this is coming from SRTM and NASA JPL. And all else equal, lower sloping areas are more suitable for siting geothermal well pads than higher sloping areas. So again, if you're really considering some given sites, this would be an important thing to evaluate, and we're making it very quick and easy to access this information. The next is Aquifer Risk. So I'm going to turn this off, and we'll look at this Aquifer Risk map. Redder areas show higher aquifer risk, bluer areas show lower aquifer risk, and please excuse, most of the world's oceans are shown as red. Those should be clipped out. But for the surface, for the land areas, you can get a sense for really what the water resources are by region. This is coming from this Aqueduct 3.0 data set from WRI, the World Resources Institute. And this is an important layer for also planning specifically different types of geothermal wells. Conventional geothermal has actually fairly high water consumption, and really open loop systems that you might imagine need to replenish water inside their underground reservoirs to ensure ongoing supply. And this makes water resources an important consideration. Actually, unconventional geothermal, so maybe more closed loop systems, they'll have more minimal water use. So really this information layer can help inform what technologies are most suitable where. So I'm going to turn some of these off and briefly discuss actually now some of our demand. So we have a number of layers that are all kind of subsets. We're exposing some of them here. But really to back up our characterizations of energy demand spatially. I'm giving a little bit of a sneak preview here. We have electricity demand rasters that, and I'll open the menu, the legend here. Bluer areas would correspond to lower existing electricity demand, and redder, darker areas corresponds to higher demand. and we're showing just here the Lagos greater area. And really, this is built on a lot of research. And I'll actually go and show the underlying layers that support those rasters, where we actually have building level demand, and you can zoom all the way into more or less the building level. And really, there's a number of data sets and considerations that go into building these layers and building up our demand characterizations that we can then use for planning. It's actually a pretty large machine learning pipeline that I'll hopefully fairly briefly introduce, and I'm happy to take questions on it after. And just at a high level, demand is important. Maybe it's clear to a lot of the audience. Really, the surface part of the equation most greatly centers around this demand. These are kind of the end users who will end up paying for and financing the use of geothermal. Really, this is the purpose for geothermal energy, to decarbonize a lot of the energy generation and the energy consumption that we have in the broader economy. So right now we're just showing demand layers in Nigeria. We have pipelines to expand this to much greater and larger areas. And what we actually start with is a view of the surface, a view of high resolution satellite imagery. And we actually make this available to some degree. Mapbox has just its own satellite image layer, similar to what you would find potentially on Google Maps. And really, this gives our machine learning models a basis for trying to come up with those demand estimates that I was just showing. And this is actually used as an input to those models. Our next model, our next input are nighttime lights. So I'm going to change this back to this dark view here and show nighttime light values. These are indicative of street lights generally and ambient lights that satellites can pick up at night. And we actually have this available as this global data set that's available. And this is coming from NOAA and NASA satellites. All else equal, you might think the greater the nighttime light value, the higher the demand, or at least the more economic activity you can sense in a given location. We also have other data sets like internet speeds. This is collected when people do things like performing internet speed tests. And if you click, you can get a sense for some of the metadata that's available. We have a number of tests, devices, average download and upload speeds. This is a proxy for wealth and income in different locations. Really, you might think the faster the internet speeds are, the greater the affordability of people to pay for upgraded internet. And there's both fixed and mobile versions of this data set. This is used as an input feature as well to those machine learning models. We have a couple of others. Actually, maybe as a little bit of a detour, we also have power lines. And this isn't used for demand specifically, but it gives us a sense for, well, if you were to actually build a well, are you close to existing transmission or medium voltage distribution grids that can help you to serve generated energy to the grid as electricity. And we have this globally available as well. The transmission data comes from OpenStreetMap, and the distribution data comes from a derived data set called Grid Finder. That's all available, and actually for all these layers, I should mention, you can find the citations for these layers here, and some descriptions for how these different layers are useful. And again, our real benefit here is that we're bringing them all into one place for really streamlined analyses and helping with screening, we hope. So now I'm going to switch to talking about those electricity demand layers a little bit more and some of the background that went into creating them. So we have demand, again, at the raster level, and we have estimates at the building level. And really, this is made available, this is made possible actually by these globally available buildings data sets that look much like what you're seeing here. So just to kind of dig in a little bit more, the polygons themselves come from Google and Microsoft. These are really pretty wonderful, globally available, computer vision derived data sets. Engineers at those companies have trained neural network models to find building polygons from satellite imagery. And since Google and both Microsoft and Bing have really expansive access to satellite imagery, they've been able to run these models and produce building footprints and building locations data sets like what you're seeing here. And really our model then goes in and tries to estimate, well, what's the likely demand based on all of these different remote sensing data features that I just mentioned, and actually a few more. So I'll briefly change gears and go back to my PowerPoint slide here. So we just discussed building level demand and aggregated raster level demand. And really, there's a couple of problems that go into our machine learning models. There's, well, electricity, really the problem is estimating electricity demand from building level features. How do you do this? There's a lot of places in the world with really actually no electricity access or meter data. And even places with electricity access may not actually have meter data available or not available to be shared publicly. And this is vastly the case for most utilities in most places. And as researchers, this is building off of a number of years of research that I did as a researcher at the MIT Energy Initiative. We have access actually to some of this meter electricity demand data. And obviously that's only for places with access currently. And we've done surveys to gather this data for a number of countries in Africa, and some in Asia and elsewhere. So really, for all of these different three cases, no access, no meter, access meter, and access no meter and access meter, we have building shapes like what I described before. That comes from Google and Microsoft. And in some places where we have meter data, you might actually have a label that says how much electricity consumption a given building has had in a month. But for all buildings, we have features like what I described before, building locations, internet speeds, nighttime lights, and actually additionally land use land class information. And the problem is, well, how do you map between all of these features that we observe and actual labels that we have? If you can train a model in places where you have meter data, you can extend it to places where you don't have meter data. Here we have the problem that actually many different buildings that might look exactly alike from a remote sensing standpoint, they might have very different consumption, at least metered consumption. And this is really part of the big challenge. It's hard to know what's happening inside of buildings from what's available and visible from space and from remote sensing data outside of buildings. And this is something that you have to contend with as well that makes machine learning difficult. Additionally, there's the problem where you might actually have multiple meters on a building, like in an apartment complex. You might have multiple buildings for a given meter, and we understand this is very common in some developing contexts where it's really a behind the meter connection. Maybe it's a detached apartment building, and there's actually no knowledge of assignment between these meters and buildings, especially in cases like the one on the right, where there's just some latitude longitude coordinate corresponding to a meter. And finally, there's a problem where there's lots and lots of noise in these meter data sets. So actually, the blue locations might be ideally what you'd want. The meters just directly over a building, or maybe someone with a GPS clicker registered a building to a meter right at the front door. In practice, there's quite a lot of noise, and it makes this mapping ambiguous. And without going into too much detail, we're developing novel methods to combine deep learning and Bayesian inference paradigms to actually handle each of these problems that I just defined. And if you have any questions about it, we can talk further. Really, if you combine these different paradigms, you can really check off these different modeling requirements. And we have a number of features. And just to kind of drive the point home, for each feature, we actually pull numbers really out of these features for each building. So imagery actually is just another feature. These are tensors of scalar values, and they correspond to really what's visible right over a given building rooftop location. And for other features, other geospatial features, we derive numerical values that correspond to given buildings. This is land use land cover. There's a key down at the bottom for different trees, built area, water, and crops. And essentially what we do is for each building, we calculate these vectors that correspond to descriptions of what's happening overhead at 50-meter resolution and at 110-meter resolution. And all of these different numeric values give us a very rich, and we think really the richest description of buildings at massive scales that really allow this analysis. So we have modeling that goes and tries to really address these ambiguities that we have between meter and building mappings. And we use state-of-the-art neural network models to go from our building features of interest and all the way down to inferences. And these are actually probabilistic inferences that go through. On the right-hand side, we have a probabilistic graphical model. And on the left-hand side, this is really the neural network engine that we use. And lastly, we show that we actually have very good, at least relative to existing and other methodologies, very good accuracies. And this absolute error is shown on the left axis. Total consumption for a given cluster of buildings is shown on the right axis. What we're showing here is that, well, we actually have decreasing absolute error as you have larger and larger clusters. This helps us to have some comfort in, while our model is more and more accurate as a percentage of total consumption, as you have more and more aggregation. So even though we talked about the problem earlier, there's some ambiguity. There's actually a lot of buildings that might look exactly the same, but have different consumption values. Well, actually, if you aggregate these buildings together, a lot of the noise that you might expect from this sort of random stochasticity goes away, and it's a demonstration in part of the law of large numbers. So just to kind of wrap up, we have a few more slides on, well, our weighted overlay analyses. So these are layers that are available as well. I'll just kind of run through them in slide format. This is for surface suitability. So we're combining our different surface data sets into just one data set that shows some high values and low values. And we're combining, in our case, different distance metrics corresponding to our demand centers. We're combining the grid information that we have and actually protected areas as well. This is a data set that we haven't actually built into the map yet, but actually you can see, at least in Nigeria, areas where there's really policies that are preventing building and likely geothermal well building in different areas. And again, we're going to expand our demand to many more places and subsequently our weighted overlay analyses. And again, this was in partnership with Google. And we actually have combined views where we're looking at both the subsurface and the surface characteristics that we described, and we map them on top of each other. And we end up with really general geothermal favorability maps. We're expanding this as well beyond just Nigeria. So I talked a lot about these existing layers. Just to quickly go over, we have some non-space heating demand that we're looking to build machine learning models around as well. We have actually, for the rest of these planned layers, identified layers that we think are very appropriate. So space heating and cooling, these are kind of like heating and cooling degree day data sets that are available. You have additional information about coal, solar, wind, hydro, electricity price information that we want to layer in as well. And as I mentioned previously, land use, land classification in protected areas. We talked a little bit about a Google partnership that we're very excited about. And just to conclude, I want to outline some ways that you can potentially work with us. So if you're an industrial organization, or you're able to engage in a data partnership, we're really looking for demand information that we can incorporate into our global models. This could be electricity demand profiles, heating demand profiles. For heating, especially for industrial purposes, we care a lot about steam temperature and pressure. And for open source contributors, we're open to collaborations around energy system modeling, data engineering, and remote sensing data sources. So with that, thanks so much. I think I may be at time. I'm happy to take a few questions if there's no time. Otherwise, we can move over to the test framework with Danny. Helen, do you have any thoughts? What's best?
You're running slightly out of time, but maybe if you could address just very briefly, how do you validate between heat and electricity demand? Because obviously Danny will talk about both, and how do we separate out?
That's great. So in terms of validating, for the electricity demand, we use a cross-validation methodology where there's a training, a validation, and a test set, and it's a very rigorous statistical analysis, only letting our models train on some subset of data, and testing and evaluating on unseen data, and this would really emulate, well, how well do you do when you actually don't have that information to train on? And we can do this across different geographies and assess generalization error. This is ongoing research. For non-space heating demand, we have a combination of bottom-up and top-down models. Bottom-up modeling is really identifying locations of interest of different demand centers, different load types, building types really. And we actually try to learn a mapping between these bottom-up characterizations and our top-down characterizations, or machine learning-driven characterizations elsewhere. And you can then use the same sort of cross-validation framework to assess your accuracy there. And actually, for space heating and cooling, this is a fairly kind of better explored literature. It's really physics-based modeling, and they use a number of assumptions, but actually, I think there's quite a lot of validation, and the error that you would have there is really based around your input data and the assumptions that you make, not just the not things like weather or anything else. So that's hopefully a brief answer. I'm happy to discuss further, and please reach out. Thanks so much.
Thank you, Stephen. So that concludes the surface and subsurface modules. Time now, probably just in time, we pass back over to Danny, who'll talk about the test tool, which is techno-economic sensitivity tool. Danny, take it away.
Thanks, Helen, Stephen. I hope that I'm able to keep all our scientists in line and following up whenever I'm going to start talking about dollars. But we have to come to the reality check of transforming all the potential, or the scientific potential, into economic viability. And that is why when we started talking about how to frame a techno-economic sensitivity tool, our ambition was to try to translate all the amazing information that we have gathered in the subsurface and surface models, how to translate that information into variables that are more on the economic viability, to translate heat flow, milliwatts per square meter, into something that a broader audience can understand, to maximize the usability of the information that we have and allow people that are going to be maybe more on the policy making, taking decisions that will support geothermal growth, or investors that want to deploy capital into geothermal, or basically just people that want to increase awareness and show the potential of geothermal in areas that may be invisible right now. So that was the framework that we used in order to develop what you're going to be seeing now as our techno-economic sensitivity tool. If you have entered the tool already, you'll see that it's a very straightforward workflow. Our ambition here was to try to break all possible barriers of entry for non-specialists in order to allow them to understand what are those variables that make a key impact in the viability of a geothermal development. And again, that's why this is more on an exploratory tool to screen areas with more potential rather than an engineering design tool that will go into the rigorosity of getting things to the latest detail, right? Considering this, our approach starts by combining the maps and identifying in the map what is our area of interest. And once you select with a click the area of interest, you will have some information coming up as the geothermal gradient, the surface temperature, and the depth to basement. Later on, the user would pick what kind of geothermal use case they would like to explore. Right now in beta, we just have the power, but we will be adding also direct use for heating, for cooling, and we also acknowledge the opportunity that geothermal can bring into storage, both heat and electricity, but that will come in a later stage. The next phase is for the user to start playing along with the sliders to define what are the values of a number of technical parameters and a number of economical parameters to explore what is the potential of geothermal application in that particular region, exploring scenarios that I would call more state-of-art, exploring other scenarios with policy incentives, with technology improvements that will maybe look at geothermal more in the midterm rather than in the short term. If I may enter a little bit on what are those models that we have inside of the tool, I wanted first to remind everybody that there is a very comprehensive user manual with all of the definitions, models, data that we have used to create this tool. I just wanted to highlight a few of them for this presentation. The first one is the temperature uncertainty. We have included a slider for temperature uncertainty, and this has come up in the subsurface module presentation, because in the end, the models that we have used up to now for geothermal temperature gradients are more focused only on conduction. They're not taking into account convection. So if you have identified an area that you know there is an anomaly or an active fault or something that will allow you to consider that the heat flow is much greater than what is reflected originally in the tool, you can increase the temperature gradient. We also have to honor the fact that at this point, considering a worldwide approach for our tool, we don't really know what are the sedimentary layers. We don't really know porosity, permeability versus depth worldwide. And that is why for now, for us, the flow rates are an open parameter for the user to explore. What we have just defined are intervals that we consider reasonable and economically viable for geothermal. And we're not considering a specific value because we don't really have the information worldwide that would allow for that. And also considering that right now we're just in a single approach, trying to be technology agnostic. We're not differentiating between hydrothermal, closed loop geothermal, fractured and engineered geothermal. So right now that's something that is not included. It will in the future, as I will explain in a second. With respect to the temperature decline, again, we were trying to strike that balance between simplicity and rigorosity, just like with any other variable. And for the time being, we have simplified to a linear decline. That, for some of the technologies, may mean that you will not allow yourself to go into the high flow rates. And this is, again, one parameter that we want to explore in the future, how to implement in a simple way, but in a way that the user can explore different technologies. And finally, the heat to power efficiency. What we didn't want the user, maybe a user that has no, let's say, a chemical engineering background or thermodynamic background, to start playing with the transformation of heating to power in any possible way. So what we do have coming from the literature is a curve of efficiency in that transformation versus temperature. What we are going to be allowing our users to do is to move back and forth, considering potential technology improvements to take that efficiency somehow higher, but always respecting the trends that we know that in order to transform heat into power at moderate temperature or at modest temperature, that's not going to be a super efficient process. If I move into the economics, how we have established the cost for the different elements that conform a geothermal project, I wanted to start with the drilling costs, where we have established a method that is, again, a simple one, considering a linear dollar per meter for the sedimentary layers, we have considered a multiplier whenever you're entering into the basement, expecting that if it's an igneous rock or a granite, it's going to be more expensive and more costly to drill further. And the value of 1,230 comes from a very well-developed oil and gas province in the US called the Haynesville, where they're actually going down to 170, 180 degrees Celsius. These are typical costs associated to that basin. And the reason why we chose this default is that probably for geothermal, it looks like an ambitious goal to reach to that level of cost. But we wanted to highlight what the oil and gas industry has been able to achieve in terms of learning curve, in terms of cost decrease over the last decade, to put a picture in the minds of people that through technology developments, we can really take the costs down for geothermal to have, let's say, more favorable economic viabilities. If I move into surface facility cost, again, we're taking a very simplified approach of dollar per kilowatt, taking data from the literature. We also add a couple of variables more related to permitting time, construction time, and capital expenditure subsidies. The first one, the capital expenditure subsidies, is to explore the impact of policy and incentives. And the second one is more on the construction of the wells and the plants, because for the time being, we didn't include exploratory cost. We wanted to consider a shovel-ready project to explore what would be the economics of that kind of situation. Again, in the future, we will explore other variables, other extremes, other considerations, including technology improvements, looking at economic, and also including the feedback of our users, because whenever we're thinking about our way forward, we have, I would say, several families of potential users for this tool, more on the policy making, more on the investor world, more on the industrial potential partners or developers. So we have a number of ideas in order to improve this tool. And you see the 3 different layers here highlighted. But what we also wanted to get is feedback from the people that are starting to use the tool in order to prioritize the different evolutions. If I quickly go through them from the technical perspective, our first approach would be to try to implement a bit more granularity on how we are approaching the different technologies that are coming up in geothermal beyond just, I have an aquifer and I produce the aquifer, such as AGS, which is the short term for advanced geothermal system, which are the closed loops, and EGS, which is the enhanced geothermal systems that mostly are associated to fracturing. In the future, we will also include an energy storage model, and we do envision the opportunity to hybridize geothermal with solar, wind, and any other potential source of renewable energy, because we do see some synergies between them. So by analyzing a more comprehensive business case, we believe that the geothermal will shine even better. From the economic perspective, we are aware that in the end, whenever we're talking about costs, these are very regional. So we would like to provide, whenever we're starting to do deep dives in certain regions, to start providing more related market prices for those regions. I think that's going to be helpful to avoid confusions. We also take into consideration that from the perspective of geothermal being deployed, it's not enough to look at the cost. It's not enough to look at a levelized cost of energy, because there are other variables that make geothermal a better choice, such as the low footprint, such as the base load capabilities that it has, such as the low dependence on minerals or other materials that may be coming from a third party. So in terms of independence, geothermal has an edge. And finally, from the perspective of considering that it's not enough to do a single point analysis, whenever we're going to be doing the full potential of geothermal, it has to be done in a regional basis to understand what are the competitive sources, renewable resources that are competing with geothermal in a particular region, in order to define what is the actual potential for a large penetration of geothermal. And finally, from the perspective of the user experience, we're aware that we're in 2023. There's something called ChatGPT and the like. That's what LLM stands for, large language models such as ChatGPT, that allow you for a much more enhanced user experience from the perspective of having the opportunity to type a question and let the program give you an answer instead of sliding up and down, back and forth between the different parameters. In terms of optimization of what you can find as an optimal solution for geothermal, we think that's going to be helpful. And of course, importing and export files, just like for the GeoMap library, that's something that will be implemented in the near future. So this is a brief summary of what we think the tool can be used for, but nothing like a demonstration to get into more the details and the different use cases and workflows that we can apply this tool. So, as I said, we always like to start with information coming from Steven, surface, and from Helen, subsurface. So, of course, every time you do a very thorough analysis with all the different layers, you can go later on to the test and do a proper analysis in a particular region, or you can be as lazy as me right now and say, well, look, if we're focusing on Nigeria and we're focusing on the area of more demand, I just need to highlight the weighted overlay analysis and understand that, of course, Lagos, in terms of demand of energy in the country, it's going to be a reasonable location to get started to analyze the potential of geothermal to cover up the demand of energy in Lagos. So if I go then to Lagos inside, and now we have moved from the GeoMap library into the test, I can zoom in into Lagos, select a location around here, right? And the moment that I select a location, you see here that you start seeing results. Surface favorability around 2, so that's considered thumbs up for new regions. Surface favorability, of course, a 5, because there's a large energy demand around the area. You see that the geothermal gradient is not massive, but we have to remember that we're talking about only conduction, meaning that if you know, as we do, that there are some areas around Lagos with anomalies, you may allow yourself to increase the temperature gradient, as I will do in a second. Before, let me just say that you also have the surface temperature and the depth to basement coming from the maps as input for you. Next thing that you would do is to select the application. And as I said, right now, we're just looking into power. Heat, cooling, and storage will come in 2024. And you have 2 parameters here that start giving you additional information, right? As I said, there's an element here of uncertainty that if you know more information about this region, you can scratch the temperature gradient and increase it to a level that is more reasonable based on the information that you have. And what we do know is that around 1 kilometer in Lagos, you have around 80 degrees Celsius, right? So I can actually consider that I'm allowing myself to vary the temperature gradient to a degree that I'm going to say that I have 80 degrees Celsius at around 1 kilometer. You see that those conditions for power production, for electricity, are not good. You see that we're not going to be producing electricity, and these conditions are reasonable price because this temperature is too low. Yeah. So basically, this case that I'm doing here will be more for heat. But if we want to explore another opportunity that is considering that we go deeper and that we go maybe to an area of temperatures around 200 that could be valid for electricity generation, you see that by doing that, what I'm doing is to define what is the target depth that I have to reach in order for this to be a successful case. The next thing that you can do is actually change the number of producing wells or the flow rate, because if you say, well, I need around 10 megawatts, yeah, you can be around here to say that your average net sales will be around 10 megawatts. No? And you can say, well, if I need more, I can increase the number of wells, right? Of course, that will have an impact on the cost, that will have an impact on the output. But the user can select flow rate and number of producing wells based on their target. What is the demand that they want to cover? The next step is to start looking at the cost of drilling through the sedimentary, the cost of drilling through the basement. And you see here that we have this shaded interval saying that, well, right now, probably drilling through basement, drilling through granite can be significantly more expensive than drilling through sedimentary rock. But there's a number of teams, there's a lot of groups working to try to decrease this cost of drilling. So maybe that multiplier is no longer a 2, it's a 1 for certain regions. Of course, if you're not in Nigeria, which is, let's say, an oil and gas province, not in the US, but you're in a country that has no industry for drilling and you don't really have a rig next to you, these values are probably going to be higher. No? So you're going to have to allow yourself for a higher drilling cost. Likewise, for the surface, you can consider a higher efficiency than what our baseline consider. You can consider higher or lower cost for the power plant. As I said, depending on, probably Nigeria is not, let's say, the most reasonable or the most extended country to have ORC turbines, so maybe you need a higher cost for the power plant. And at the end, what you can do is to explore what kind of subsidies will support in those early stages the development of geothermal, the deployment of geothermal, because you will see that whenever you're changing something, the economics, the construction time, the discount rate, the subsidies, what we're going to be changing is the payout price, right? So if you want to have something lower than 100, you can play around with the sliders and understand what's the impact of policy in a particular country, in a particular location. What is the impact of a technology improvement in that location? What we did not want is to stop there at the LCOE. We wanted to add at least a couple of ideas of other parameters that should be considered. First of all, the emissions that you're reducing, the CO2 that you're not emitting because you're working with geothermal, but also the surface footprint, which in terms of renewable energy, geothermal always ranks in the lower tier of how much footprint you need for a particular deployment of, let's say, 14 megawatts, as I'm showing here. That's use case number one. If I move into, let's say, enough of Africa, let's maybe go to Europe. We can take a look in France as a country that does have geothermal industry, maybe more focused on heat production than electricity. So I was just playing around with the parameters around the area of Strasbourg. You see here that we do have a subsurface favorability of around 2. Again, that's a thumbs up. We don't have the surface favorability because that's still focused in Nigeria for the time being. We have a very nice thermal gradient that we know that in this region is somehow a little higher. Okay, so if we're able to take into consideration all these parameters, we can go into the current status of this area, where this field, where you have around 170 degrees Celsius of production, you have one production well, you have a modest production of flow rate per well. As I said, we would have maybe higher cost than usual for this region. And you see that in terms of where we're landing, it's around $200 per megawatt hour, which is more or less the target that Susuforet had initially. And it's also the reason why around Europe, whenever in Germany, Croatia, in other countries, they're paying a premium for geothermal. They're staying at these levels in order to facilitate the acceleration of the penetration of geothermal inside of the EU. The last example that I wanted to do, and I will remember to change and share correctly right now, thanks Helen for that, is if you want to go maybe to an area like the USA, where maybe your focus is more on trying to identify what are those regions that have potentially more boreholes, which means that there's already studies being done in those regions, that you have very good characterization of the subsurface because you have drilled for oil and gas. You can do that as well. So I can, again, based on the analysis, selecting a location maybe near to San Antonio, I can go again to the test tool. I can select again the USA. I can go around the area of San Antonio and start exploring maybe regions that, as I pointed out here, that have maybe a depth to basement that is sufficiently large, let's say deeper, that you're going to be always drilling through sedimentary rock. You may have information, or you may build information that allows you to detect anomalies that would simplify your life by allowing you to have a target depth that is, let's say, 6 kilometers, not 8 kilometers. And if you're intending to produce electricity, you can again play with your flow rates. You can say that I'm in Texas, so maybe my drilling cost scenario for sedimentary is even lower than that. I'm maybe at $1,000 per meter in certain regions of the US, and start considering what are those, let's say, subsidies or IRA, or what are those conditions that even with a larger discount rate would allow you to be competitive in a region like Texas, where you have probably a lot of competition from gas, a lot of competition from other renewables. That's what we had in mind as demonstration of the tool, these 3 use cases. So I think it's maybe the moment to take some questions in the last minute of this meeting.
Yes, you have one, Danny, from PS. is asking if we are planning to add some parameters like ERR and PV based on electricity or heat price.
Yeah, from the perspective of having a more comprehensive economic assessment, those are some of the variables that we will have in the maybe in the output, but also, as I said before, we're planning to have an export file that will delve a little bit more on the parameters. This is more an exercise to start selecting what is the optimum. Later on, whenever you are deploying or exporting a final solution, an output file, there will be more granularity into the economic variables and also the technical variables. That some of the parameters are more on the fixed assumptions that we have made. They are going to be explicit in the output file.
Yeah, and there is a small question from Soraya Bonas to understand why finally by default we have this 1 kilometer horizontal section.
Yeah, I'm laughing because that's part of our internal discussions on how to break a balance between having default values and having elements that we would maybe allow the user to play with. Our vision is to consider that horizontal wells have been magnificent for the oil and gas industry to increase productivity. So we do envision that, I mean, of course, if you have a volcano and you have a 1 kilometer well and you have 200 degrees Celsius there, probably you don't even need this tool. You don't need that horizontal section. But whenever we're trying to deploy this worldwide in a more scaling anywhere, the use of those horizontal wells are going to be needed, particularly in sedimentary basins. But you're right that that's a parameter that we have lengthy discussions internally. We'll probably end up having that opportunity to give flexibility to it.
You have one more question, Danny. Sorry if Valerie didn't at the top. The expected delivery dates on the other stages.
We're working now to deliver heat as soon as possible because we do consider that there's a lot of potential in showing not just power but heat. Cooling and storage will follow, and we also consider that at least the LLM capabilities, that's something that we want to deploy as soon as possible. So through the year, there will be several releases that we will just try to post to the larger community as soon as possible.
Maybe really the last question, again from Soraya, it's regarding the potential competition of gas and other renewables. Yeah.
That's why in our roadmap, we do want to talk about geothermal penetration modules. That kind of analysis cannot be done, I believe, in a single point analysis. We need to take the region. We're exploring different open access code that does this kind of assessment that would allow us to explore in a particular region what would be the penetration, assessing the competition of gas, renewables, and coal and any other in that particular region.
Yeah, I think that's all.
Excellent. Let's maybe just remind everyone that the tool is open for use. It's open access. It's for free. So please use it, play with it, and let us know if there are questions, comments, anything that you may want to communicate to the developer teams. We're here to help. We're here to try to make these tools as useful as possible. I'm going to pass the word maybe to Stephen, Helen, if they want to close out with some final remarks.
Well said, Danny. Thank you so much, and ditto.
No, just to thank the extended Phase 1 scientists for joining us today and addressing the questions, and to everyone else that contributed to the conversation. Thank you. And yeah, feedback, enjoy the tool, and send any other questions, send them through.